Okay, we are now at Sideling Hill, which is one of the many high ridges running down the Appalachians. The Indians that lived in this part of the world called these the Endless Mountains because you can trace these ridges for hundreds of miles. This particular ridge is a layer of rock, sandstone, conglomerate, shale, and siltstone, clastic rocks that have been folded downward into a trough. And you can see that in the outcrops out here on the side of the road. The rocks themselves are, as I say, all clastic, and this actually is a record in the rock of the history of what was going on 100 miles to the east of here. The rocks in this part of the Appalachians start out with sandstone at the bottom, then there's a thick layer of limestone for many, many tens of millions of years. Now we crossed that in the Great Valley. We came down off the Blue Ridge. It's a broad, 20-mile wide valley underlain by limestone and dolomite. So that was low country, low enough so that the ocean flooded into it. Then the Appalachians began to go up when an offshore volcanic island arc was pushed westward and collided with the rest of the North American continent, raising the tectonic mountain range. You put up a mountain range, it immediately starts to wear down. All the stuff that erodes from that mountain range washes off the mountain into the ocean and fills it up with sand and mud and gravel, and you have a section of plastic rocks. As long as the mountains are there, the plastic's coming off. Starting off coarse rocks, and then as the mountains get lower and lower, finer grained material, until finally the mountains are gone. And then you get another sequence of marine rocks coming in, limestones. We're going to get to see that in our third stop. Then, a chunk of rock about the size of Madagascar came in and collided with North America in the northeast. That one again raised a very high mountain range called the Acadian Mountains. Acadia is the old name for Nova Scotia. Those are the mountains that provided this clastic material here. This is part of what's called the Catskill sequence. The Catskills, Poconos in New York and Pennsylvania are made of exactly these same rocks. And you can follow those rocks, this layer of plastic, all the way into the interior of the continent as far as Illinois. They too wore down and were gone a short time after these rocks were laid down. One of the thickest layers of limestone follows this, and those are the limestones that Mammoth Cave is made in Kentucky. So that's a second mountain range raised up, back down again, and it's recorded in the sediments. Every time you get the mountains, you get the plastic rocks. When you don't have the mountains, it's limestone. Then finally, at the end of the Paleozoic, Africa hit. The biggest collision of all, and the old ocean went away entirely. You could walk from here to Morocco without getting your feet wet. Of course, you'd have to climb glacier-capped mountains to do it. The glacier-capped mountains were back over that way where Washington and Baltimore are today. They too wore away completely. We ended up in the Mesozoic. And we had the ocean come in then too. But in the Mesozoic, the supercontinent of Gondwana, which resulted when the old ocean closed, split apart again. And we had then the Atlantic opening up. Okay, now these particular rocks in here, up on the top there is quartz rich sandstone and conglomerate. We can't get up there. Well, I suppose we could if we were hiking up the ridge here, but we'd never get the rest of the field trip done if we did that. Oddly enough, before you think about it, this is a down fold. We're in the trough of the fold here, where it's folded like this. And you can see the rocks dipping back this way on the far side, dipping this way here, and at the lowest point in the middle. It's a down fold, but it's a ridge. Okay, why is that the case? It's counterintuitive. The reason is because of the down fold, the most resistant rocks, which are right at the very top of the ridge here, were low enough so that they were preserved, and because they were preserved and are the hardest, they wear down the most slowly, and so they make the ridge. Where the rocks were folded up, softer rocks were brought to the surface, and they wore down faster, and so you have valleys on either side. Now, one very interesting thing here, immediately across from us, just up the slope from that blue sign on the other side, you can see a layer of darker rock there. That's an old river valley, about the size of the Monocacy River that we crossed back there, where the river, which was laying down all these sediments, cut back down into the earlier sediments when the channel shifted, and the channel is still preserved there. The river then moved again, filled up the old channel with new sediments, and that's the channel filling that you see over there. Now, the fact that these rocks are so well and obviously bedded indicates the conditions here were not constant. If this were deep sea sediments, that doesn't change much. From day to day, from year to year, from century to century, conditions in the deep ocean are pretty much the same. So you don't see very different layers. Here, we have all these different layers. That's because conditions change. You have a flood. You might have 2 floods in a year. That's going to be 2 thick beds of sandstone that are laid down in the side of the river. When the river shifts, you get channels, but the channels move. Nothing is constant over the centuries, over the millennia, and so you get very, very different layers of rock laid down. On one of the other field trips I take, we get to see the deep water rocks that were laid down off the edge of the North American continent, and you can't see the bedding in it because there weren't any changes. It was always the same. Okay? Any questions here? You can see, by the way, once you look at these rocks, you don't have to worry in identifying the rocks. You don't have to say, oh, is this igneous, metamorphic, or sedimentary? Everything here is sedimentary, so you don't have to pick and choose. It's fairly obvious what you're looking at. Some of these rocks are more conglomeratic. There is conglomerate up in the higher levels there, quartz pebble conglomerate. That's when the mountains up to the east pushed up a little bit higher, and you got coarser material coming off. If you look at the thickness of these rocks and you measure the thickness here, you measure the thickness further west, you measure the thickness further east, the thickest rocks are towards the east near the Blue Ridge. The reason for that is that when the mountains were going up to the east because of the collisions going on, they piled up layer and layer on top of one another because of the collision. That actually bent the crust of the earth down. The Himalayas, for example, 29,000 feet high. That weighs an awful lot. It weighs so much that the Indian crust, the Indian continental crust, is actually pushed down thousands of feet. And because the crust is a little bit rigid, that leaves a hole in front of the Himalayas, many thousands of feet deep. That hole gets filled in with material washing off, and the deepest hole is right next to the Himalayas because that's where the weight is. It gets less and less as you go back southward into India. And so the thickest sediments in the Ganges Valley, and that's the Ganges Valley I'm talking about, are right in front of the Himalayas. And it's 3 miles of sediment deposited in a 3-mile deep hole. Well, if it's a 3-mile deep hole and there's 3 miles of sediments in it, it's basically at sea level. And then you look to the north and the mountains are 6 miles high. Well, yeah, that's the weight that's causing the crust to sag. The same thing is going on here. If you look at the sediments of the late Paleozoic, they are 2.5 miles thick now, and that's after you've worn a lot of them away. That is right next to the high mountains that were to the east. You don't get the sediments preserved there. Well, yeah, because there was no hole there. That was the high mountains. You wear stuff away. You don't deposit it. You wear stuff away in the hole in front. Then, well, where are those mountains today? There are no glacier-capped peaks over there today. Well, yeah, they're gone. They wore away. Okay, if you sit on a mattress, the mattress sinks. When you get up, when you take the weight off, the mattress goes back up again. So the highest mountains in Maryland are actually in the western part of the state now, the stuff that was at sea level during the time the mountains were being built. The mountains are gone, and so the hole has pushed back up again, and those sediments deposited in the hole are now lifted back up. So that's where the highest mountains are now. It doesn't make sense until it's explained and you see what's going on. Okay, is that clear to everybody?
Guess it will be on the next test.
Well, yeah, they've already, the last lecture was on the geologic history of Maryland, and I covered much of this during that lecture. Okay, let's go on and we'll get to our next stop, and we'll get to look at some red beds a little bit lower down in the section than here. It's a little bit earlier. So, onward.